node has been, so do one BFS from an arbitrary node, find one node which is the last node that has been visited, and then again start BFS from there and find the most extreme node from this node. You can prove that if that is, although there might exist other diameters, this greedy procedure would also find the diameter. So it just comes down to three cases where that is proof by contradiction, where assume there was a diameter, it intersects this. You can just take the common portion and prove it. Okay, so another way of finding diameter in graph is using dynamic programming. Diameter in tree is using dynamic programming, which is theta and dp. So as he said, maximum root will be endpoints of any one diameter. What about minimum?
It should lie on the diameter.
Okay, he says it should lie on the diameter. So which point on the diameter?
If there are odd number of vertices on the diameter, middle one, otherwise any of them.
All right. So yeah, we have the solution. There is, if it's 3, then of course the middle one, and if it's 2, then any one of these two. That is, the minimum level we can assume diameter is d. The minimum level we can get is just d by 2 seal. Okay. So now Venkatesh will discuss DFS and other properties.
Okay. So the problem is, you are given an undirected graph, say and you are given some edges of this graph. So what you have to do is, you have to assign direction to each of the edges. Say, so for this edge you can either assign this direction or this direction, or direction. Okay, you have to assign direction to the edges and also some weight to the edges, so that all the paths from any node to node 1 have the same cost. Okay, as an example, suppose for this node, okay, assume all these directions are present. So for this node, one solution would be, okay, for this node, suppose these two edges are 1 and 2, and these 3 edges are 1 and, okay. Yeah, for this node, assume these 2 edges are 1 and 2, and these 3 edges are 1, 1 and 1. Then this is a path from this node to node 1. This is a path from this node to node 1. Both these paths must have equal cost. That is, there may be many more paths from this node to 1. So basically, if you have this assignment, all the paths from this node to 1 must have the same cost, same total cost. So that from any given node, all the paths from the node to 1 will have the same total cost. You got the problem, right? Everyone are clear with the problem?
But are we solving for a specific node or for every node in general?
Every node. You have to assign the weights for every edge, so that take any node, take all the paths from that node to 1. All these paths must have the same cost. But from this node to 1, the cost is 3. But from this node to 1, all the cost is 2. Okay, so the solution is like, you do take the graph in the undirected sense. You do a DFS from, okay. Yeah. So take the graph in the undirected sense. You do a DFS from node 1 to all the nodes. So okay, I'll explain what DFS is and then explain the solution. So DFS depends on, first you have to formulate the problem. So the problem is clearly formulated here. All the nodes and edges are explicitly given, so you don't have to explicitly specify the graph here. You don't have to explicitly formulate the problem here. The problem is clearly given in this case, but in the case like the matrix he discussed there, you have to clearly formulate the problem like nodes are the cells and edges are all horizontal and vertical. So one important thing in DFS is you have to avoid infinite loops. Like in DFS, by nature you will go in the order of their levels, so you won't be having infinite loops. But in DFS there is a slightly more possibility, but even that can be avoided if you code a little clearly, code more clearly. So this is the pseudocode for DFS. It will almost be like DFS, except that instead of a queue it will be a stack, and you will push instead of enqueue and pop instead of DQ, I mean, pop instead of the pop there. So the algo for DFS will go something like, I will explain for an undirected graph. So for an undirected graph, so assume I want to DFS from 1. So the algorithm will be like, you have a stack, you will also have a scene. So first scene of all the nodes will be 0. Scene of all the nodes will be 0. So initially you encounter 1. You will first do scene of 1 to be 1 and push 1 into the stack. So let the stack be S. So the stack just has 1. So this is the initial before loop, that is the case before loop. So once you enter a loop, you pop the top element of the stack. So it is 1 and the stack is empty now. Now you have 1. Consider all the neighbors of 1 in this graph. So they are 2 and 3. So 2 and 3 are the neighbors of 1. So update scene of 2 and 3 to be 1 if they are not seen already, I mean. So if they are not seen, you don't have to consider the node again because you have already seen them. So update scene of 2 and 3 to be 1 and push 2 and 3 into the stack and continue again with 2. So in the next iteration, what will happen is you take 2, see all the unseen neighbors of 2, which in this case 1 and 3 are already seen, so you don't have to consider them. So the only unseen neighbor of 2 is 4. So take 4, do scene of 4 to be 1, remove 2 from the stack and put 4 into the stack. So next 4 will come, check all the unseen neighbors of 4, it's only 5. So pop 4 out. So update scene of 5 to be 1 and push 5 into the stack. So you can see that although 2 and 3 were pushed at the beginning itself, 3 hasn't got its chance yet. So that is the meaning of depth first. You go depth wise first, come back and then go to the next level. So you will basically, you can see that it forms a tree kind of structure. So the tree will be given like, first we visited 1, from which we put 2 and 3. From which you put 2 and 3. From 2 you put 4. And from 4 you put 5. Okay. So this is the main item.
Don't you just put 2 from the, like after 1,
Okay.
You just go to DFS 2, you don't visit 3, right? By the time you visit 3, you'll have already visited 3. If you choose the path 2,
Okay.
you end up visiting, the 3 should come under 5, right? The DFS tree. 1 to 2,
You don't visit 3. The minute you reach 2, you traverse the 3 for 2.
Okay.
Yeah, you traverse the
What?
3.
Yeah, that is 2, 3 would come, this is undirected, right? 3 would come in 2 subgraph.
Okay.
In fact, 3 would come in
So this is just a line.
line.
Yeah.
Okay. Okay. Yeah, it's okay. I mean, so in this case you just get a, okay, 4, 5, okay, some other example.
Make it a tree. Let's say in some place. Make it a tree. Cycles in some place.
Okay.
This one traversal would be 1, 2, 3, 5 and 4.
Yeah, that depends on whether you see 3 first or 4 first. Okay, never mind, let this be. So 1, 2, assume the traversal is 1, 2, 4, 5 and 3 itself. So for this problem, what we are going to do is, for an edge connecting I and J, we will have both I and J in this DFS tree. We will assign the cost of this edge to be difference in level between I and J. So in that way, you can see that for each node, either you will take a tree edge, in which case this all tree edges will have a path of will have a cost of 1, since the difference in levels will be 1. So you either take a tree edge, or if you take an edge like this, the cost will be 2, which is equivalent to sum of these two costs. So you will never so the cost of all paths from any node to 1 will be the same if you assign the weight of an edge to be the difference in levels. Okay, you got it?
And in this problem, should you do the DFS in considering the graph to be undirected, or considering the graph to be reversed?
Consider the graph to be reverse, not undirected. So we'll discuss some properties of DFS. So first is the parenthesis theorem. Okay, what it says is, first of all, when you do a DFS, the first time you visit a node, you can give it a time saying a start time. That is, start time denotes that this is the first time I visited this node, and when you leave the node from the DFS, you can assign it a end time. So for example, I'll write a short DFS code. So suppose it is void DFS of int I, if not scene of I, return scene of I equal to 1. If scene of I return scene of I equal to 1. So start time of I equal to time plus plus, and then for each neighbor V, do DFS of V, and then outside the loop do end time of I equal to time plus plus. So what these denote is, start time of I denotes the first time you visit I. So this time is called the starting time. This is the first time you discovered the node, and then you DFS the subtree below it. So for each neighbor V, you DFS V, and this is the time where you leave I. So you do end time of I equal to time plus plus. So this is basically, so start time of I denotes the time in which you entered the node, and end time of I denotes the time in which you left the node. So what is the parenthesis theorem? Do anyone of you know what the parenthesis theorem is?
If you take if you represent the start and end interval by an opening and closing parenthesis, the nested or they don't intersect at all for any two vertices.
Okay, the idea is correct. So for a given time, if it is start time, you denote it by opening parenthesis, and if it's an end time, you denote it by a closing parenthesis. So for each time interval, check whether it's the starting time of anything. If it's the starting time of at least one node, you denote it by open parenthesis, and if it's the ending time of at least one node, you denote it by a closed parenthesis. So for each time interval, if you do it, you will get a set of open and closed parentheses, correct? So you may get something like this. What this is this will form a proper parenthesis, proper parenthesization. That is, for each start node, for each open parenthesis, there will be a corresponding closed parenthesis, and this closed parenthesis will, the time which the closed parenthesis occurs will denote the end time, will be the time which denoting the end time of this node. So basically, this is a proper parenthesization as discussed by Gaurav yesterday. I mean, he discussed for catalog numbers, he discussed what a proper parenthesization is. So this will form a proper parenthesization. So this essentially says that for I mean, so when you go